Hello, my name is Frédéric Girard. I am a PhD student at the University of Zurich in the astroparticle physics group of Professor Laura Baudis. Our group is composed of 20 members involved in one or more of the following experiments: xenon, Darwin, Gerda, and Legend. These 4 experiments have one thing in common. They are all low background experiments deployed underground to shield themselves from cosmic radiation. Xenon and Gerda are current experiments operated at the Laboratori Nazionali del Gran Sasso, or LNGS for short. The underground laboratory was installed in a tunnel passing under a mountain in Italy and currently hosts 17 experiments. Legend is a near-future experiment also located at LNGS, aiming to detect neutrinoless double beta decay in germanium-76. Finally, Darwin is a next-generation dark matter and neutrino observatory proposed to be operated at LNGS. I am a member of the Darwin collaboration, and today I will show you around our lab space at the University of Zurich. The R&D setups you will see are all involved directly or indirectly to the success of our large-scale experiments using liquid xenon dual-phase TPCs. In the quest for the direct detection of dark matter, dual-phase liquid xenon time projection chambers, or TPCs, have become some of the most sensitive devices to weakly interacting massive particle interactions. The detection principle is simple. An interaction between a particle and the xenon atoms results in the emission of VUV light and the release of electrons. Arrays of photosensors at the top and at the bottom detect the prompt scintillation light called the S1 signal. Meanwhile, the electrons are drifted along a uniform electric field produced by 2 electrodes and shaped by a cylindrical drift gauge. The electrons reaching the top array are extracted into a high electric field region in gas xenon. The interaction of electrons with the gas produces a secondary scintillation signal called the S2. We use the ratio of the S1 and the S2 signals to distinguish electronic recoils, mainly produced by charged particles or photons which release more electrons, from nuclear recoils produced by neutral particles such as neutrons and WIMPs and releasing less electrons. Furthermore, we can determine the position of the interaction in the detector by reconstructing the position in the horizontal plane from the S2 hit patterns in the photosensor array. The depth of the interaction is deduced from the time measured between the S1 and the S2 detections. We can therefore systematically fiducialize the sensitive volume in the detector and remove events caused by radioactive decays in the detector materials. At the University of Zurich, our group members are active in multiple aspects related to dark matter searches, from simulations for detector geometry optimizations and background reduction, to studies of our detector's sensitivity to dark matter and other physics channels, such as neutrinos and neutrinoless double beta decay. We also actively participate in the massive R&D effort needed to build and operate large detectors facilities, such as Xenon 1 ton, Xenon N ton, and the future Darwin Observatory. The setups I will show you today are a small-scale TPC, 2 photosensor testing facilities, and a full-scale Darwin demonstrator. Let's start. The first setup we have here at the University of Zurich is Zurich 2. This is a small-scale TPC used to measure properties of liquid xenon as well as to test calibration techniques. You can see in this computer-aided design drawing the typical TPC components: the field gauge, the photosensors, and the electrodes. The walls are made of a solid block of PTFE, which acts as a reflector, which increases the total light collection in the photosensors. The drift region is 31 millimeter in diameter and 31 millimeter tall, making this our smallest dual-phase TPC. At the bottom is a 2-inch photomultiplier tube, or PMT. PMTs are light amplification devices which have been used for decades in low background experiments for their high gain, low noise level, and their fast response time. So how do they work? Well, the PMT is a vacuum tube usually made of glass or quartz. The end window is coated with a photoreactive material, the photocathode. Photons can eject electrons from the glass surface into the vacuum via the photoelectric effect. An electric field produced by two electrodes held at different potentials accelerates the electrons towards a series of metal diodes where the impacting electrons release multiple secondary electrons. This process is repeated in subsequent diodes, resulting in an amplification by 6 to 8 orders of magnitude of the primary signal. In Zurich 2, we use the PMT as a trigger as it covers the full bottom area, maximizing the light collection. In the top array, we find another type of photosensor, silicon photomultipliers. These are solid-state sensors composed of thousands of reverse bias single photon avalanche diodes operated in Geiger mode. This means that a photon interacting in a cell produces an avalanche with a set number of charges, generating a signal proportional to the number of impacted cells. This gives silicon PMs an excellent single photon resolution. Two photons impacting the same cell at the same time will, however, output the signature of a single photon, making the response of silicon PMs truly linear only at low illumination, when the probability of two photons impacting one cell is low. Silicon PMs have advantages over PMTs. They potentially present a lower intrinsic radioactivity, are less expensive, and don't require a high voltage when in operation. On the other hand, they suffer from an extra noise component called dark count, which are signals produced when thermally generated avalanches are triggered in the cell. Since these dark counts have the same signature as single photons, this noise component is a nuisance for low energy events. The dark count rate can be reduced by operating the sensor at lower bias voltages at the cost of lower gains. Since dark count events are time uncorrelated, the requirement of coincident triggering of multiple sensors in a detector can help to reject purely dark count events. In Zurich 2, we demonstrated for the first time the operation of silicon PMs in a dual-phase liquid xenon TPC configuration. The array is composed of 16 6x6 square millimeter sensors, each coupled to a ×10 preamplifier directly on the silicon PN base. This helped to improve the signal-to-noise ratio at the cost of an extra 3 watts of heat input, which needs to be compensated by the cryogenic system. Speaking of cryogenics, Zurich 2 uses a simple and reliable liquid nitrogen-based system where a cold finger dipped in liquid dissipates the heat from the cryostat, providing enough cooling power to liquefy the xenon at about -100 degrees Celsius. The temperature and pressure in the cryostat are controlled with a heater strip installed on the inner vessel, controlled by a PID controller. The cryostat is vacuum insulated to eliminate conductive heat transfers, while a super insulation limits radiative heat transfer. The gas system is used to handle the gas xenon. While not in use, the gas is stored in gas cylinders. To fill the detector, the gas is simply transferred through a pressure reducer and directed to the vessel where it is slowly liquefied. To put the xenon back in the bottles, we evaporate the liquid in the inner vessel, which is transferred to the bottle by a process called cryopumping. The bottle is immersed in liquid nitrogen, and the gas freezes inside, producing an underpressure, which makes the pumping process. Included in the gas system is a purification loop, but we'll discuss this later. The final purpose of the gas system is the introduction of calibration sources in our detector. A typical calibration source is krypton-83. Krypton is the decay product of rubidium-83, which is stored in solid form in a stainless steel container. Krypton is introduced in the system by flushing the decay chamber with the recirculated xenon. Krypton-83 has a half-life of 1.83 hours and decays by emitting 2 photons at 9.4 and 32.2 keV, emitted in an interval of about 156 nanoseconds. This makes for a characteristic dual peak signature, which is easy to tag in the data processing. Zurich 2 was recently used to test a new calibration technique using Argon 37. Argon gas encapsulated in quartz vials was irradiated at PSI in Switzerland with neutrons to produce the Argon-37. The argon decays via electron capture, accompanied by Auger electrons of less than 2.82 keV. This makes for a low-energy calibration source, ideal for low-threshold experiments. The next two setups I will show here are used for photosensor testing. As you can see by simply looking at current dark matter experiments, photosensors play a major role in the hunt for dark matter by basically being the eyes of the detector. Needless to say, before commissioning sensors at large scales, our collaboration tests a multitude of sensor variants to ensure their high sensitivity at the wavelength of the light we want to detect, in our case in the VUV range. We also need to ensure their reliability in the long term and to ensure that their noise levels are low enough to make them sensitive to low-level signals. The first of the two setups is the liquid argon setup, LARS. This setup can be used to operate sensors in liquid argon, mostly for R&D purposes performed by our Gerda and Legend members. But we can also use this setup with gas nitrogen or gas helium as a way to do simple temperature-dependent measurements of photosensors. The gas is cooled down by flushing liquid nitrogen in a copper coil, and the chamber temperature is controlled by varying the flow of liquid nitrogen. For Darwin, we use LARS to test new types of silicon PMs in the search for a suitable replacement for PMTs. The test chamber is composed of a reflective PTFE housing with silicon PMs mounted to the lid. A blue LED is installed at the bottom, used as a triggered light source of controlled intensity for gain and breakdown voltage determination. Silicon PM's parameters measured include the thermally generated dark count rate, the crosstalk rate, which is the result of secondary photon emitted in the primary photoavalanche being detected in a neighboring cell, and the after pulsing rate, which is the result of an electron being trapped in the silicon crystal being released at a later time, producing a second avalanche. Marmotex is one of three facilities designed for testing photosensors before they were deployed in the Xenon 1-ton and the Xenon N-ton experiment. The cell can host up to 10 3-inch PMTs, which are tested for gain and to check for leaks at liquid xenon temperatures. Gas seeping into the vacuum tube can cause electric breakdowns and sparking, leading to the premature death of the sensor. In all, 105 PMTs were tested in Marmotex for Xenon 1-ton and Xenon N-ton. Marmotex is built in a similar way to Xenon 1-ton. The gas system is similar to the one I showed previously in Zurich 2, with storage bottles for the xenon and gas handling system equipped with the same xenon gas purifier. The main difference lies in the cryogenic system. Marmotex uses a pulse tube refrigerator, or PTR, to liquefy the xenon in the cryostat. Helium gas is slowly compressed and expanded by a piston, exchanging gas at one end of the tube in the heat exchanger. The cold end of the tube is thermally coupled to a copper cold head onto which the xenon is liquefied. Again, the PTR provides a set amount of cooling power, and we control the temperature of the cold head with a heater strip and a PID controller. As I mentioned before, Darwin is a next-generation experiment. This means that to increase its sensitivity compared to its predecessors, Darwin will be much, much bigger. Comparing with the current Xenon N-ton detector, Darwin, in the current conceptual design, will be about twice as large both in diameter and height. This size increase comes with new engineering challenges. For instance, the electrode meshes, or wires, might experience sagging, which would be detrimental to the homogeneity of the electric field. Our Darwin colleagues at the University of Freiburg in Germany are therefore building Pancake, a full-size Darwin demonstrator in the XY direction. This facility will be used to test full-size prototypes of electrodes and to measure the homogeneity of their electric field. The increased height of Darwin raises another challenge. After electrons are released in the xenon, they are drifted towards the top anode. Electronegative impurities in the liquid xenon, such as water, oxygen, or carbon monoxide, only to name a few, absorb electrons as they drift. The survival fraction of electrons can be expressed as a function of the number of impurities and the drift time. Since the maximum drift distance in Darwin will be double that of xenon Anton, we really need to efficiently remove the impurities from the xenon in order to maximize the fraction of electrons reaching the top of the detector. We therefore built at the University of Zurich a full-scale Darwin demonstrator in the Z direction, the Xenoscope. With this, we aim to demonstrate electron drifts over 2.6 meters and study physical phenomena necessitating such a long drift region, such as electron cloud diffusion. Xenoscope was designed and assembled by our team of PhD students and postdocs of the astroparticle physics group. But the construction of the demonstrator facility was really made possible by the incredible support and knowledge of our mechanical workshop and electronics workshop at the Department of Physics of the University of Zurich. This facility is not much different than the small-scale setups we have here, but is bigger and better. The heart of the system is the vacuum-insulated double-walled cryostat. The inner vessel is made of electropolished stainless steel to help the outgassing process, where trapped gases are released from the wall surface. It can contain up to 350 kilograms of xenon, operated at a temperature of around minus 100 degrees Celsius at a pressure of 2 bars absolute. The top flange of both cryostat vessels are suspended below a leveling system, which provides a fine adjustment of the XY level, a feature which is important for controlling the parallelity of the liquid surface to the electrodes of the TPC. The xenon is liquefied in the cooling tower, mounted directly on top of the top flange. A 200-watt PTR cools down the copper cold head, machined with fins to increase the surface contact with the xenon gas. A viewport installed on the side of the cooling chamber allows us to monitor the liquefaction of the xenon. This proved useful to observe freezing of the xenon gas on the copper surface, which was reducing the efficiency of the system when the temperature was set too low. The cryogenic system is complemented by a heat exchanger system, without which it would be impossible to perform fast recirculation of the xenon in the purification loop. In the small-scale setups we have seen before, the xenon is recirculated in a gas-gas configuration, where warm gas was taken from the cryostat, recirculated, then brought back directly to the cryostat. In Xenoscope, we extract liquid xenon and direct it to the heat exchanger, where it vaporizes. The latent heat needed for the vaporization is provided by the returning gas, which exchanges the heat in the heat exchanger and liquefies. We can see here at the back the liquefied xenon coming from the heat exchangers. The purified xenon drops in a funnel, which carries it all the way down the cryostat. This creates a natural convection where the cleaner xenon is located at the bottom and the dirtier xenon is at the top, ready to be extracted to the purification loop. When not in use, our xenon can be stored in 10 aluminum gas cylinders. These are suspended to load cells, with which we can measure the total mass of xenon in the storage system with a maximum uncertainty of 100 grams. 4 of these bottles are sitting in liquid nitrogen dewars to perform cryopumping. The gas system of the demonstrator serves several purposes. The first is the purification loop. We use ceramic filters at the inlet and outlet of the heat exchanger to catch large particulates which could be present in the gas system. The xenon is circulated by a dual diaphragm compressor into a hot metal getter. the zirconium filter element is heated to 400 degrees Celsius and absorbs electronegative impurities, leaving the xenon gas with an impurity level lower than 1 part per billion. The second function of the gas handling system is the filling of xenon gas from the storage system to the cryostat and recuperation back to the bottles. High pressure gas from the storage system is transported to a pressure reducer, allowing us to slowly add xenon to the cryostat where it is liquefied. At the end of normal operations, which can last from several weeks to several months at a time, we can use the gas system to carry the xenon back to the storage vessel in a controlled manner by cryopumping. The last purpose of the gas handling system is to perform pressure-dependent automatic recuperation. If, for any reason, the pressure inside the cryostat or at any place in the gas handling system was to exceed the safe operational value, check valves would open and direct some gas to a gas cylinder in the storage array, which is always kept frozen. The system allows us to safely and automatically reduce the pressure in the cryostat without loss of xenon. In the event that the pressure relief to the bottle is not sufficient and that the pressure increases uncontrollably, a pressure relief valve can open and vent gas to the atmosphere to prevent the burst of any part of the system. Recuperation of xenon by cryopumping can be a very long process, estimated to be over 1 week long for our detector. Our solution to this problem is BOX, ball of xenon. This is a pressure vessel rated up to 90 bars, large enough to store up to 450 kilograms of xenon at room temperature. Filling of the detector is done in the normal way. The recuperation, however, can be performed via gravity. The procedure is simple. BOX is pre-cooled with a copper cooling block, cooled with liquid nitrogen. When the pressure in BOX is about the same as in the cryostat, a cryogenic valve is open, allowing the liquid xenon to flow from the cryostat to the pressure vessel. The gas section of BOX is open to the gas section of the cryostat, equalizing the pressures, allowing the system to self-regulate the liquid transfer. When the liquid transfer is finished, the remaining gas from the cryostat can be transferred to the gas storage system by cryopumping. Inside the cryostat, we plan to operate the detector in 3 phases: a 50 centimeter purity monitor, a 1 meter TPC, and finally, a full 2.6 meter TPC. All 3 phases are made of the same modular detector, making it longer simply by adding up modules. The purity monitor is similar to the time projection chamber, but is operated in a single liquid phase and relies on charge readout. Its purpose is to measure instantly the purity of the xenon. First, electrons are produced by a photoelectric effect on the photocathode at the bottom by flashes of UV light coming from a xenon flash lamp. The released electrons are drifted towards the anode at the top, traveling through 3 regions. In region 1, the drift of the electron produces an induced current on the photocathode, read out by a charge readout. In region 2, a portion of the drifting electrons is absorbed by electronegative impurities. Finally, the electrons reach region 3, where they induce a current in the anode, again read out by the charge readout. The ratio of the charge read in the charge readouts can then be used to calculate what we call the electron lifetime. This can in turn be directly interpreted as a measurement of the xenon purity level. The TPCs we will deploy in phases 2 and 3 are essentially the same detector. The charge readout at the top will be replaced with a silicon photomultiplier array. These are the same sensors that we have used in Zurich 2, but 16 channels are grouped and read out together. Such a tile creates a photosensor of increased size, reducing the number of cables and wires in the detector, but also increases the dark count rate per channel, which, for large arrays, could lead to accidental coincidence. The TPC is also fitted with a liquid level control system. As mentioned before, the tilt of the cryostat is corrected by the XY leveling system. The height of the liquid level must also be adjusted to optimize the light yield of the S2 signal, which is produced when the electrons are extracted in the gas phase. We then adjust the liquid level height with the weir. Two concentric metal cylinders make up a bucket of some sort. This container is immersed in the liquid, which can spill over into the weir through a small opening at the top of the inner cylinder. By adjusting the height of the weir, we then adjust the height of the liquid. We can monitor the height of the liquid level to sub-millimeter precision by measuring the capacitance of 3 cylindrical capacitors installed at 120 degrees around the head of the detector. As mentioned before, in the time projection chamber, the electrons are drifted with an electric field. We produce this field by biasing the electrodes with a negative high voltage at the bottom, a positive high voltage at the top, with the gate being kept at ground. The challenge of producing such an electric field lies in the making of the high voltage feed-through, where the high voltage cable passes from air side to the gas xenon side. Here at the University of Zurich, we will produce and test custom-made prototypes of electric feed-throughs for Darwin. We will produce these feed-throughs by cryofitting the components, a process where the conductor, dielectric material, and ground shield are machined to tight tolerances and cooled down with liquid nitrogen so they contract and can be assembled. As the materials warm up, they return to their original sizes, making a leak-tight assembly. For the demonstrator, we designed a comprehensive slow control system. The slow control is the brain of the detector facility, monitoring all parameters of the experiment. Our slow control uses open source software such as Grafana for the user interface, Prometheus for data ingestion and alarming management, as well as our own proxy service providing the necessary security level for the integration of the slow control to internet. This allows us to monitor the detector facility from anywhere in the world and even control remotely some sections of the gas system, such as the activation or deactivation of the purification loop, the adjusting of the recirculation flow, and if needed, the manual triggering of recuperation process. I hope you enjoyed this small overview of our lab space at the University of Zurich. The experiments and testing facilities you have seen today represent only a small portion of all the work which goes into the making of a dark matter direct detection experiment. Our collaborations count hundreds of scientists all over the world who work hard every day to make dark matter detectors always more sensitive. Will we one day succeed in detecting dark matter? No one knows for certain, but one thing is for sure. We, at the University of Zurich, will continue to push the limits of liquid xenon detector technologies with that goal in mind.